We continue on with part 2 of forces. We've just been through a whole bunch of different force summings, and so you've seen hopefully all of part 1, and now we're going to continue on with our fourth example, this time a flat surface moving to the right with friction, but this time the applied force is at some angle theta. So first of all, let's do that. It says to the right, so I have a push to the right or a pull to the right, and I'm going to say it's a pull to the right, and it's pulling at an angle now. And this is our applied force. I'm just going to call it F1 for simplicity's sake. And it's being pulled, yes, ladies and gentlemen, at some angle theta. Other forces acting. Well, we have the normal force acting up, Fn. We have the weight acting down, which I will call mg. If the object is moving to the right, the frictional force opposes us. There's my force of friction. So here is my sketch. Now it is time to do some force summing. Some of the forces in the x direction. Now here's where you got to be careful. Notice how force 1, F1, is having a force in the x direction, F1x, and a force in the y direction, F1y. We have to compensate for both of those. So, positive forces first. Well, that's part of F1 in the x direction. So what's F1's force? Well, I'm looking for this F in the x direction. What is it? Well, force in the x direction is the adjacent side, so that's going to be F1, oops, I didn't mean to write that in red, F1 cosine of our angle theta. What other forces are acting in the right direction? Or, I'm sorry, in the x direction? Well, we also have the force of friction, minus force of friction. That's all of our forces in the x direction. This is going to be equal to the mass times the acceleration in the x. Some of the forces in the y direction. Let's take a look at positive forces first. And the first positive force I see is part of force 1 that's acting in the y direction. So F1, this is going to be opposite sides. This is related by the sine of theta. I see the normal force plus, because it's going up, the normal force. And I see mg going down, so minus mg. Now, do I know if it's accelerating in the y direction? Well, if it's something like a wagon that you're pulling or a box that you're pulling across the floor, as you pull on an angle, generally speaking, those boxes don't pop up out of there. So usually their accelerations are 0. But going to the generic form, our default, we'll say that's equal to the mass of the object times the acceleration in the y direction, where usually this is going to be 0. In this particular case. All right. Next one. We get to our first angled surface. Angled surfaces, no friction on this. And now here's where things get somewhat convoluted. Let's draw forces acting on this. First of all, let's talk about gravity. Which way does gravity act? Well, gravity acts usually, and I can't believe I just said usually, but always acts straight down on these diagrams. mg. Always. Next force we have that's acting on it, well, that's the normal force. Now, in every other example we've done, it's been on a flat surface. This is not a flat surface. The normal force is acting perpendicular to the surface. So I have some kind of angle, theta here, and the normal force is not acting straight up. So if you draw your normal force like this, I am sorry, you're not right, because that is not perpendicular to the surface that it's sitting on. Instead, we draw it like this. And if you imagine this going straight down like this, this is a 90-degree angle. That is perpendicular to the surface, and that is our normal force, Fn. Next thing we draw in here, there's no friction, and we're saying there's nothing else acting. Sweet. That's a piece of cake now. Let's take a look at our sum of the forces. And here's where we get very careful. Whenever we have angled surfaces, there's danger of missing something, which I will highlight here. Sum of the forces, x direction. Well, now we have to define what our directions are. In the past, we've been using a normal coordinate axis, just like we've been taught before, plus x, minus y, minus y. But now on an angled surface, that tends to break down a little bit. And believe it or not, it's actually easier if we rotate these axes, and instead we do an axis where the x-axis is parallel to the surface of our incline. So this will be plus x, and this will be minus x. Then our y direction is plus y like this, and minus y like this. And yeah, that looks complicated, but it actually makes these problems quite a bit easier. Remember, our standard coordinate axis, we get to pick it, and in this particular case, we're going to pick something wise. And I'm telling you right now, it's wise to pick it so that your x-axis is parallel to the surface of the angled incline. So, some of the forces in the x direction, so we're talking about in this direction right here. What forces do we have acting? And you might say, well, it doesn't look like we have any. Well, this is where we have the issue. You see mg is acting straight down. That's not in the x and that's not in the y. And it turns out part of the weight is acting in the x direction and part of the weight is acting in the y direction. So what we have to do is we have to learn to break this up. So we have mg right here, and we need to break this up into components. And we're going to draw a line perpendicular and then a line parallel. This line right here is perpendicular to the surface, and this line right here is parallel to the surface, so that is a 90-degree angle. And if we do that, this angle right here is the same as this angle right here, and so this is angle theta. So now, what I'm going to do is I'm going to erase a little bit. I'm going to get rid of this arrow. I'm going to get rid of this arrow right here. What does that mean for the sides of the triangle? Well, the blue weight is the hypotenuse. So this over here is the weight, and I'm going to abbreviate that now, W. This is the weight in the y direction, and this is the weight in the x direction. And what do those equal? Well, in the x direction, notice how this is opposite side. So this is going to be mg sine of theta. Y is adjacent, so that's going to be mg cosine of theta. This is one of those times when I talk to you about most of the time x goes with cosine and most of the time y goes with sine. When you're doing angles, that doesn't happen anymore. So we've broken the weight down into components. Some of the forces in the x direction. Weights acting down the plane. Now, in my convention, that's acting in the negative x direction. There's no forces acting in a positive x direction in this particular case. So I don't have any positive forces. So I start off with a negative, and I write this as mg sine theta, taking this sign right here. No other forces acting in the x direction. That must equal mass times the acceleration in the y direction. Without friction, that box is going to accelerate down the incline. And if I knew what the weight of the box is and I knew what the angle was, I could calculate that acceleration. Need some practice on that, I understand. Some of the forces in the y direction. Well, up forces, we have the normal force, Fn. And then we have the component of the weight in the y direction. That's acting down. Remember, negative y. Minus mg cosine theta equals. Now, remember it's tilted. Is the box going to be accelerating in our y dimension? Remember, our y dimension is this direction right here. Is it going up or down in the y direction? And the answer is no, it is not. Sum of the forces is equal to 0. All right, let's do our, I think, last one. Nope, got 2 of them. That's supposed to be number 7. Number 6, this time we got an angled surface. This time we got friction. All right, let's draw forces in here. We're going to label it just like we've done it before. Center of mass, weight acts straight down. Normal force acts like this. I have friction this time. Friction is going to oppose the motion, FF. Next thing I do when I draw my picture is I know my weight has to be broken down into components. If this is angle theta, perpendicular dotted line, parallel dotted line, so that this is a 90-degree angle. This right here, and I realize I just made my MG really bad here. This is MG. This side right here will be the hypotenuse, MG. This is angle theta. This is going to be cosine of theta. And this is going to be MG sine of theta. All right, take some practice to learn how to draw those. There's my forces drawn in, and I've broken down my MG into components, so now it's force summing time. Sum of the forces in the x direction. I would like to take my positive forces first, and this time my positive force going up the ramp is the force of friction, F. Coming down the ramp is my component of weight minus mg sine theta equals. That'll be equal to the mass times the acceleration in the x direction. Sum of the forces in the y direction. In the y direction, we'll do in green I forgot to label this one. This is the normal force. I have the normal force acting up, so we'll say Fn. And I have mg cosine of theta acting down, so minus mg cosine theta equals, and as I said before, it's not going to be accelerating in our y direction, because remember our y direction is moving like this. That's our up and down in this particular orientation, 0. And our last picture here, I have an angled surface. It is with friction, and this time I have an applied force at some kind of angle theta. What I'm going to do is I'm going to say that that force is acting up the ramp, even though it doesn't specify. So here is my force 1, my applied force, and I'm going to break it up into components. Notice we have a little bit of an issue already, because some of F1 is in the x direction and some of it is in the y direction. So I break that up. This is my angle theta. This angle down here can be different, and so I'm going to call this conventionally angle phi, or phi, however you want to pronounce it. Two different angles now. I have friction, so if I'm pulling the box up the ramp, my friction will be acting down the ramp. So friction is going to be acting this way, force of friction. My weight is acting down, mg. My normal force is acting up like this, Fn. I'm going to take my mg and I'm going to break it up into components. This is a perpendicular dotted line. This is a parallel dotted line. This is a 90-degree angle. This angle matches this angle down here, and so this is angle phi. And everybody loves these because I got two different angles going on, so we really have to pay attention to what's going on. We will do the x direction in, let's do purple. Sum of the forces in the x direction. Well, what's going in the positive direction in our x direction? Well, F1 is going up the ramp, but it's actually part of it. So if I go over here, and on my dotted line, this is angle theta right here. This would be F1 cosine of theta, and the y direction would be F1 sine of theta. So in my x direction, I have F1 cosine theta up the ramp. What's going down the ramp? Here's where you got to watch carefully. I have the force of friction going down the ramp, and I have a component of the weight going down the ramp, which you got to watch for. I got this side right here going down the ramps. When the person is pulling up the ramp here with F1, it has to fight the friction and the weight component. So this is mg. Now, this is opposite of angle phi, and so this is going to be sine phi. And this over here is going to be mg cosine phi. And so I'm worried about the part that's going down the ramp in the x direction. So this is minus mg sine of angle phi. And what does that equal? That equals ma in the x direction. I got that really condensed there. All right. Next up, in green, we will do the sum of the forces in the y direction. Sum of the forces in the y direction. We have Fn obviously going up. Also going up is this part of the force 1. It's pulling up. So that's F1. So plus F1, and that's sine, and I'll put that on the board so you can see it, of theta. And acting down in the y direction is this part of the weight. So minus mg cosine of angle phi, or phi, whatever. That is going to be equal to, well, ideally, our object shouldn't accelerate in the y direction. We could say it's equal to mass times the acceleration in the y direction, but conventionally, we just say it's equal to 0. Once you're able to understand how to find the sum of the forces every time, this is how we go about problem solving. There is no one particular formula to use. Every situation is different, and that's what makes this a little bit on the trying side. But we'll have lots and lots of practice. Thank you for your time. Have a good day.